Good morning, all of you. In today's session, we are going to start with 10th standard chemistry and physics, and where unit 1, reflection of light on the curved surfaces, series 6 is going to be started, right? Earlier, we made different series on this unit 1 only. So each series consists of the compressed concepts of this unit 1. So here, detailed explanation of all these series are available on the channel called World of Competitive Chemistry. Let us enter into our today's concept. So here, ray diagram for the convex mirror. In the earlier series, we gone with ray diagrams for concave mirrors. By changing the position of object, what will be the change or what will be the modification in the position and the size of the image. That kind of relation was studied in the previous session. Now we entered into ray diagram drawn for convex mirror. Convex mirror stands for what? That is the having bulged outside surface which enlarged outside and which used to give the image of that particular object in the smaller size, right? So this is the kind of system where we have the curvature outside, which is called hyperbola. Parabola is for concave mirror and hyperbola we can denote for this convex mirror, right? So here it is possible to draw the ray diagram for this convex mirror too. So let us see what are the rules which used to govern this kind of ray diagram of convex mirror. In order to explain that, we have three consisting rules. One is called the rule 1, where we are going to start with the ray, that means R1 called incident light, which is parallel with respect to the principal axis, right? So this used to fall on the convex mirror. So after that, it used to reflect on the point F. F is denoted as a focal point and reflected back in the manner where it is moving through this mirror and which used to reflect in the backside manner. This is a rule 1, where light originated from the source is used to travel and meet at the point of mirror, and later it will be reflected on focal point and reflected back, bounced back in the opposite direction. This is a rule 1. In the second rule, we are denoting this ray 2. That means incident light is denoted with R2. Ray 2 can be originated from the object which used to fall on the surface of the curvature. You can say it is a convex mirror. Later it will fall on the same point called the focal point, and in the same direction it is moving back with the parallel line with respect to the principal axis. That is called the condition 2. Rule 2 denotes what? So that is exactly reverse to the rule 1. So where we are going to start the ray that is denoted as R2, traveling in the direction towards the focal point, and after the reflection, it will be parallel with respect to the axis. With respect to the principal axis, it will be the parallel line. So that is called a rule 2, which is represented in the figure number 18. Now, let us move on to third rule. In the third rule, we are starting from the ray or object, incident light from the object. So that is denoted with R3. R3 is moving in certain direction and heated on the surface of the convex mirror. Later, it used to concentrate at the point called center of curvature. See, denoted for what? Center of curvature. After reflection at the center of curvature, it will be bounced back in the exactly same direction without any angle. In the same direction it is moving, in the same angle it is moving, but in the opposite direction. Initially it is moving in the forward direction. After bouncing at the center of curvature, again it is moving in the opposite direction on the same path. So this is denoted as a rule number 3. A ray traveling in the direction of center of curvature will, on the reflection, after bouncing at the point of curvature, what happens? It will be traveled in the opposite direction and appears to be coming from the center of curvature. It will be started from the center of curvature after bouncing at the point. See, so it will be in the opposite direction. This is denoted as a rule number 3. Now, let us see how can we apply these rules. What will be the use of all these rules in our daily life? So let us see here. Here is the convex mirror and we place the object at the point called AB. AB is the position of the object which used to generate two rays. One is called R1 and another is called R3, because we are going to combine both the rules called rule number 1 and rule number 2. rule number 3. That's the reason why here we are applying the rays like R1 and R3. One is originated at the tip point and hitting at the surface of the convex mirror, and later it will be focused on the focal point, which is obeying exactly rule number 1. And another, with a certain angle, it is moving and reaches the center of curvature point. Later, it will be bounced back in the same opposite direction, right? So, when these two light rays are converged at the point called A prime and B prime, there is a origination of the mirror image. There is a origination of the image is possible, but when compared to the original one, it will be the diminished. The size will be extremely low. You can clearly compare both the things. A, B is the larger, and here you got the image of the shorter one. And whatever the direction of that image is there, in the same direction, this image is also generated. And the third thing is, when you're applying these light rays, if you're getting image on the screen, that is said to be a real image. But in case of this, when the object is placed at the point AB, it is hitting on the convex mirror. Now the image formed beyond the convex mirror A prime and B prime, this is said to be a virtual image formed on the mirror. Hence, you can say it is the virtual image. This is clearly visible in the figure number 20. Object is placed at the point AB and used to generate the two light rays said R1 and R3. We are going to implement two laws called rule number 1 and rule number 3 combinedly used to be implemented here. Here you can clearly observe that one ray is moving in this direction, another ray moving in this direction. So R3 is a reciprocal. R3 is a reciprocal. Reciprocal in the sense forward as well as backward direction on the same path. So here rule number 1 and rule number 3 both are implemented together, so that we got the image of that object behind this convex mirror A prime, B prime. This image will be generated virtually, and which is called a virtual image because it is generated on mirror rather than the screen, right? So this is the application of the rules which implied for ray diagram for the convex mirror. Now you can extend this kind of experiment to various applications by changing the position of this object. Initially, we place the object at the distance or at the certain distance with respect to the convex mirror at the point AB. Now you can change the position of that object so that you will get different kind of images, and that practical observation you can do that. And one more question is given, that is the extension of the statement which is given just now. So what is the question? So as we are changing the position of object, is there any change in the position of the image? So is there is a change in the position as well as the size of that image? Can you find any relation between the object distance with respect to image distance? Object distance denoted with U, image distance denoted with V, right? So here, is there any relation between that? So if you are changing the position of that AB from the existing distance to shorter one, so is there any change in the position of image? That kind of explanation is given in this graphical form, which is collected from the topper. And here, U versus V, we are going to plot. U is nothing but object distance, V is nothing but image distance, right? So when we are changing the position of object distance, there is a reciprocal change in the image distance is possible. This is denoted with this curvature, which is called a hyperbola. Right outside, you can consider that is called a hyperbola. So as we are moving towards the origin point, what happens? There is a reciprocal increase. That means as we are decreasing the distance of the object, there is a exponential increase in the size of image generated is possible. That is clearly denoted in the graphical form. If it is very closer distance, exactly at the point of 2F, F is nothing but what? Focal point. If this what object placed at the point of 2F, that means a double of the focal point. Now you will get the image of equal distance. Whatever the distance of object is there, in the equal distance image will be originated. This is a point one we have to remember. And the second is, if the object is exactly at the focal point, the image generated at the infinite distance. We are not able to measure the distance exactly. Far away beyond that convex mirror, you are able to get its mirror image. So that is a kind of observation which is drawn in accordance with changing the position of object and changing the position of image. This is the information gathered from the topper. Thank you very much. And next is about another derivation, right? So derivation of formula for the curved mirrors. When we are taking this convex mirror, object is placed at the distance of AB, and that used to generate two light rays. One is moving in the parallel path with respect to the principal axis, and that used to bounce at the surface of convex mirror at the point X. And the second light ray is generated that is used to migrate in certain angle, passes through the center of curvature. The second ray is passing through the center of curvature and bouncing on the surface of convex mirror exactly at the point of Y, right? So these are the conditions we are going to apply, and we are going to derive the equation with respect to this ray diagram of the convex mirror, right? So in order to derive the equation, so first let us see ray diagram from the top of B. So here in this ray diagram from the top of B, we are going to generate the rays, light rays used to originate at the T point of this object B, right? So with respect to principal axis, now we are going in the parallel manner. Parallel light ray is moving and hitting on the surface of convex mirror at the point of X, right? After hitting, what happens? It will be reflected. It will bend in certain angle and passing through the focal point F. That reflected light is passing through the focal point F and reaches to the point called B prime. So here B prime, it used to passing through the B prime point, right? So this is the condition 1. Let us move on to another ray. So here from this point B, another ray is also generated that is moving in certain angle, not exactly parallel. With a certain angle it is moving and passing through the center of curvature. After passing through the center of curvature, it used to strike on the point Y on this convex mirror. So on the point Y, it is striking. In accordance with the previous rule number 3, what you can observe, when it passing through the center of curvature, so it will be reflected back in the same angle with opposite direction. That's the reason why. It is very clear that here you can observe the arrow moving forward as well as arrow moving backward. Because when any light ray passing through the center of curvature, that used to bounce back in the opposite direction with the zero angle, right? So again, it is moving. While moving back, it used to converge with the light ray reflected from the point X. So that convergence at the B prime point is possible. Whenever the convergence or combination of two light rays are possible at that point of view, you can find the image. Image formation is possible. With respect to the object, the image formed will be inverted. If object is a vertical, right, it will be in the opposite direction. And the size of image formed will be diminished. It will be very smaller in size. And the image position will be A prime and the B prime, right? So this is the condition what we are going to apply here. Based on this kind of application, now we are going to draw the diagram. Now we are going to draw the equation. So here two light rays are passing XB prime. XB prime is the reflected light from this parallel light ray. And YB prime is the light passing through the center of curvature, are meeting at the point B prime. So this is the point of convergence. B prime is said to be the point of convergence. B prime is the image of B. So here you will get the exact image of this AB object. So here we will get the, wherever convergence is there you can get the image. So AB is the object, A prime, B prime is the image of that one. Now we are going to apply the mathematical fundamental delta ABC. Delta ABC is nothing but that is a triangle. So ABC is used to form a triangle, right? So that is exactly is equal to A prime B prime C. A prime B prime C is also another triangle which is originated with respect to this image. So ABC is the triangle with respect to the object. A prime B prime C is the triangle with respect to the image formed. So both are exactly similar, right? So according to that, here we will draw one kind of specification. What is that? The distance AB by distance A prime B prime. That means AB by A prime B prime is equal to what we can say, AC by A prime C. Whatever the distance AB by A prime B prime is there, AC by A prime C will be exactly equal. So this is one kind of assumption. And second is about x p prime. X p prime in the sense we are starting from this x and p prime was taken here on the principal axis, right? So this distance exactly is equal to AB. This distance is exactly is equal to A prime B prime. So based on that, we are going to again apply the mathematical fundamental delta P prime xf. Delta is nothing but triangle P prime xf. This is one kind of triangle that exactly is equal to A prime B prime f. A prime B prime f. These two triangles are equilateral, are equivalent in nature, right? So based on the same assumption as mentioned in the equation number 1, we are going to draw the equation number 2 also. How can we draw? P prime x. So this distance P prime x by A prime B prime is equal to P prime f, this distance P prime f by A prime f. So this distance by this distance. Okay. So that is the second assumption which is mentioned in the equation number 2. Now let us move on to continuation of that one. P prime x is equal to AB. P prime x is equal to AB because this distance exactly is equal to this, because both the lines are parallel. This is said to be a principal axis. This is said to be a light ray originated from the T point of this object. So these two distances are exactly equal. So based on this, it is very clear that AB means this objective distance by A prime B prime. This is the image distance is equal to P prime F by A prime F. P prime F by A prime F. Right? So this is the another assumption. So from this is the equation number 3. This is the equation number 3. So from this we can infer that. So let us combine equation number 1 with equation number 3. Equation number 1 says that AB by A prime B prime is equal to AC by A prime C. So AB by A prime B prime, here also AB by A prime B prime are there. So when these two having another relation, so that these derivatives also having equal relation. So we are going to draw that AC by A prime C is equal to P prime F by A prime F, because we are going to combine both the equations 1 and 3. So that new derivation got generated in the equation number 4. AC by A prime C is equal to P prime F by A prime F. This is a new relation, right? If the paraxial rays denotes what? The rays which are traveling closer to the principal axis. With respect to principal axis, if any rays are going in the closer proximity, those are called paraxial rays. They are considered, you can say P prime coincide with the P. P prime coincide. P prime here, P prime is on the screen, P is on the mirror. So both are exactly equal. So that is applicable when paraxial rays are considered, right? So that we can replace P prime with the P. P prime F is equal to PF. Now the equation will be AC by A prime C is equal to PF by A prime F, right? So from this equation figure number 21, it is clear that the distance AC is nothing but, in the triangle we have A is the object origination point, C is the center of curvature. That AC is equal to PA minus PC. This is equal to P to A minus P to C. So in this way also you can measure this. Now AC prime, A prime C. So this distance AC prime is equal to what you can write in the similar manner, we can write as PC minus PA prime. PC minus PA prime. So this is another inference. And third is about A prime F is equal to this distance. A prime F is equal to PA prime minus PF. PA prime minus PF. So these three are the values of AC, A prime C, A prime F. So these three values can be inserted in this equation number 5. In equation number 5, we have AC, we have A prime C, we have A prime F. So if we substitute all these values in the equation number 5, the equation can be represented as PA minus PC. PA minus PC, why? Because AC is equal to PA minus PC, right? That's why PA minus PC by PC minus PA prime is equal to PF by PA prime minus PF. Just to be inserted the values of AC, A prime C, A prime F in this equation, right? So now let us concise the equation. PA can be denoted with U. What is U? Just in the equation, you know, U denotes what? U is nothing but object distance. U is nothing but object distance. V is nothing but image distance. So let us insert these values. PA is equal to, this PA is equal to object distance. PC is equal to R. PC is called. So this P2 center of curvature is called R, and that value is called 2F, and PA prime is equal to V, that is the image distance, and PF is equal to F. P to F is equal to F. So these are the concised values of this ray diagram of the convex mirror, so that we can insert all these. PA is equal to U. U minus PC is equal to what? 2F. So U minus 2F can be inserted. PC means what? PC is equal to 2F minus PA prime is equal to V. U minus 2F by 2F minus V can be taken, is equal to PF. PF value is F. F by PA prime is equal to V. Then PF is equal to F. F by V minus F. Now what we will do? We will apply cross multiplication. So these two, numerator, denominator get multiplied. Denominator, numerator get multiplied. This is called cross multiplication. Now we are going to apply U minus 2F into V minus F is equal to F into 2F minus V, right? So this denominator when go left side, it will be multiplied. And this denominator go right side, it will be multiplied. So that we will get the extended equation. And still we can expand this equation. How can we? So here two bracket terms can be multiplied together. So that U into V, UV minus 2F into U into V, UV minus U into F, UF. So U term can be multiplied with these two. Now we are going to apply this. Minus 2F into V, it will become minus 2VF. Minus 2F into minus F. Minus into minus, it will become plus. 2F into F, it will become 2F square is equal to F into 2F, 2F square, F into V, VF, right? So here, 2F square minus VF. In this way, we are going to expand the equation. After expanding, what we will do? Let us take similar terms one side. What similar term? All F terms can be taken on the one side, one direction. Except UV, remaining all are having F term. That's why we will take all F terms in the one direction. UV is equal to, so here already right hand side we have two parameters. One is 2F square minus VF, they remains as such. When minus UF goes right hand side, it will become plus UF. Minus 2VF, it will become plus 2VF. Plus 2F square will become minus 2F square, because left to right sign inversion is possible. Right. Now we will cancel out all the opposite terms. Plus 2F square minus 2F square get compensated. Both get cancelled. Plus 2F square minus 2F square get cancelled. Minus VF, and here we have plus 2VF. So 2 multiplied with VF means 2 times VF is there. That means one VF get compensated with one VF. One more VF will left here. So the equation is UV is equal to UF. UF is not cancelled, right? UF plus one more VF is there. UF plus VF. UV is equal to UF plus VF is the concise equation for the entire derivation. Now, this equation 7, this is called equation 7. This equation 7, on both the sides we are going to divide with respect to UVF. and both ends you are going to divide with UVF parameter. So that UV by UVF is equal to UF by UVF plus VF by UVF. Both sides just we are dividing with this UVF common term. So UV by UVF is UV get cancelled, right? Here we have UV, here also UV is there. Both similar terms get cancelled. It will become 1 by F. UF by UVF. U get cancelled. F get cancelled. What is the leftover term here? 1 by V. Only the term remains is 1 by V. Here V get cancelled. F get cancelled. 1 by U left here. The finalized equation is 1 by F is equal to 1 by V plus 1 by U. U is the image distance, sorry, object distance. V is the image distance. F is nothing but combination of PF. So here principal axis, focal point, this distance is called F. So 1 by F is equal to 1 by V plus 1 by U. This is the finalized derivation for the convex mirror ray diagram. This is called a mirror formula. This equation, final equation, what we got, you can denote it as a equation number 8. That is called as a mirror formula. By using this mirror formula, the sign convention can be utilized. So this can be applied in the various regions too. So by this, the series 6 of 10th class chemistry and physics unit number 1 was completed. Hope this session will be helpful for you. The application of ray diagrams towards the convex mirror and the derivation of the relation between the convex mirror with respect to the object distance. This entire derivation is detailed discussed. So this session will be helpful for your preparation. Thank you very much for your patience listening. Thank you one and all.